This is a short recorded lecture on thinking a little bit more deeply about reliability and validity in the context of measurement theory, and specifically in the context of sort of latent variable modeling. Oops. So historically, and what you probably learned in a research methods class in the past, is this approach to reliability and validity, which I call the psychometric approach, but it stems from what is historically called classical test theory, or CTT. Classical test theory is a whole assembly of ideas that came about in the 50s and 60s in psychology, that gave rise to the word psychometrics, actually, and which is what we've been seeing thinkers like Joel Michel are sort of so against, right? But classical test theory has been incredibly useful, and it has been maintained and is taught, and has these ideas of reliability and validity, such that reliability is generally seen as some measure of consistency, either of measurements or scores. So consistency of scores or measures over time and settings, and then internal consistency of items. So the homogeneity of a set of indicators, or homogeneity of a set of items. And that's pretty much all we ever talk about when we talk about reliability. And then, of course, the more thorny issue is thinking about validity, and trying to answer the question of whether or not a measurement, or more typically a test or an instrument or a scale, measures what it's supposed to. So, you've heard me talk about my struggles with this concept in general, and we've discussed a little bit in class so far this idea that validity is from the new perspective, of the new realist perspective, that validity is, as conceived of in the psychometric or classical test theory approach, is a little bit of a slippery slope, right? Like, validity measures generally are correlational, so correlational with respect to some other measures that measure the same thing, or some gold standard. So that's the sort of the classic approach, and we're going to spend a couple of slides reviewing that quickly, but then we're going to kind of contrast that with a more modern measurement theory take on reliability and validity, and specifically a more modern take using the models and the methods of structural equation modeling. So I borrowed this slide from another slide deck, and I'm sorry that I can't credit it appropriately because I don't remember where it came from, but this is a nice visual depiction of reliability, the way it's sort of conceived of in classical test theory. At the top, there's this notion of like going through time, so that arrow with a T on it. And you can see questionnaire 1 and questionnaire 1 that are measured at different times, right, is an assessment of retest reliability. Questionnaire 1 and questionnaire 2, measured across time or at the same time, are something that we call equivalent forms reliability. This is kind of an old expression, equivalent forms reliability. This is reliability now, not validity. So we're not talking about, benchmarking questionnaire 1 against questionnaire 2 to bring to bear some validity evidence. We're just talking about reliability. So the extent to which one questionnaire can be considered reliable, it can be benchmarked against a second questionnaire with items that are assumed to come from a comparable pool of items. So when you think about conceptualization of a measurement space and the whole pool of indicators that might be available to fill out that conceptual space, if some of those items are on questionnaire 1 and some of those items are on questionnaire 2, then what you would be assumed to have would be equivalent forms, right? If those indicators are indeed equipotent indicators of the same phenomenon, if you randomly divided them between measures, then those measures should be very highly related to each other, right? And in terms of reliability, that's called equivalent forms reliability. there's a whole branch of classical test theory reliability analyses that have to do with this notion. And we're not going to learn them in this class, but they're things like the Spearman-Brown formula, which is this idea that you could use this split half or equivalent forms reliability coefficient to do some interesting stuff. There's the, oh, I don't remember what KR stands for, but there's a set of analyses that you can do that are also benchmarked on that. And this is where the idea of coefficient alpha comes from, or Cronbach's alpha, which is the idea that all of the indicators or all of the items on a measure, on a scale, should be highly correlated with each other. And then if you take the average inter-item correlation, you get something called alpha. And that's what's shown, although the arrow is in a slightly weird spot, but that's what's shown in the upper left for questionnaire 1, the extent to which items within a single measure are themselves correlated with each other. So these are ideas of reliability that are pretty common in classical test theory. The bottom one, those are supposed to be people. And so there's this other notion of reliability, not as occurring as a phenomenon about items that are answered by a group of people, which is a person-centered idea of reliability, right? You get 100 people, you get them to take questionnaire 1, questionnaire 2. An equally important idea of reliability is the extent to which people would agree on their ratings of something. So, rating phenomena, we've been talking about a little bit. Ratings are generally applied to different kinds of phenomenon, behavioral phenomenon, rather than self-report phenomenon. And it is important to know the extent to which people who are rating some external thing, like a behavior, like teamwork or safety, are in agreement with each other. So that's the classical test version of reliability. This is the classical test version of validity. So, and I borrowed this from the same slide deck. I think this is a really nice slide. This says, if you think about conceptual variables, and by conceptual variables, that's sort of the psychometric language for what we might call reflexive latent variables, right? Like real but inherently unobservable phenomenon. In the CTT framework, they are often called conceptual variables. And so this is just saying, how might you think about whether or not your measurement of some conceptual variable really measures what you think it does. And that's the whole notion of validity. So you would want to know that your measurement of the conceptual variable is predictive of future behaviors. And that's that arrow at the top. You would want to know if your conceptual variable is related to other measures of the same conceptual variable. You would want to know if your conceptual variable is related to other self-reported measured variables that purport to measure the same thing. And so you can see this depiction sort of is trying to highlight the different forms of validity that you probably learned or were taught. And I want to say here as a side note, if you Google measurement validity, you can find there's the Stanford Handbook of Social Sciences. There's a very highly regarded William Trocum book. You can go to Wikipedia. You can pull up 10 different resources to ask the question, what are the different forms of measurement validity or test validity? And you'll get 10 different answers, which generally means that there's a problem, right, in a scientific endeavor. If everyone has a different idea about what something is or how it should be carved up or how it should be assessed. And so we've touched on that a little bit with this idea that maybe correlational evidence isn't sufficient evidence for validity anyway, that maybe just knowing that something is what it is sufficient. So that what we're seeing, and I think it's interesting that we might be learning this at a time when there's a lot of really interesting scholarship going on around let's just overhaul our notions of what validity is. Having said all that, you will recognize the names that are about to come up, right? Face validity, content validity, convergent validity, which is the extent to which items of your measure are correlated with the items on another measure that's purported to measure the same thing, similar items or scales. Discriminant validity is the extent to which items on your measure or the measure as a whole are not related to something other items on other scales that are not supposed to measure the same thing. Predictive validity, is what it sounds like, right? Can the measure predict future things, either future behaviors or future self-report measures? And concurrent validity is the extent to which your items or measure as a whole are capable of being benchmarked against some other version of the same thing. So the ideal version of that is when you can get a completely different measure of the conceptual variable, like a behavioral measure, and look at that with respect to self-report. But as you guys know, what often happens is just for concurrent validity, the self-report measure is benchmarked against another self-report measure. So these terms are not bad. You probably have heard others, right? Concurrent, divergent, discriminant, predictive. Sometimes you'll see that called like criterion validity. And again, I'll just say the fact that there are so many different names for these things is indicative of something, and probably not something great. So what we're going to try to do is update our thinking about reliability and validity a little bit. And I'll just say also as an aside that much of this new work came about in the early 90s when the computational ability to solve large systems of simultaneous equations became pretty widely available. And structural equation modeling, which is SEM, became a widely used analytic modeling approach. And so what we've sort of been seeing in class, and what I sent you guys a week or so ago, which was that discussion on that listserv, that is an SEM listserv, the structural equation modeling listserv, that was started by Ed Rigdon, who's an active participant there, who in fact I'm sure was pretty well represented in the threads that I sent you. And so this is a slowly, we know in academia and science, things change very slowly, but so this is a changing but slowly changing field. And so these ideas are still somewhat formative, right? There's no textbook we can go to and look at and say, oh, this is the answer to how we're going to think about reliability and validity now in this new model, in this new world. But we're going to touch on it a little bit of overview. So, we know when we take a measure, an observed measure, there's going to be error in it. And in the past, we didn't know what portion of error was systematic and what portion of error was random. So random error is okay, right? But systematic error is not okay. Now we might have some methods for trying to tease out the difference between systematic versus random error, and we can use those methods to do a better job of thinking about what reliability is. In this new way of thinking about it, reliability might be assessed by nothing more than just test retest, and we're going to take a closer look at that. So test retest reliability means, does your device or measurement produce the same score within the same individuals over time, over repeated testing situations? So we're going to take a kind of a deep dive on that. The issue of updating our thinking about validity is a little more complicated because validity itself is a complicated notion, and it's entrenched so deeply with the 50 years, 60 years of the history of psychometrics and philosophy of science, and we talked about the nomothetic net. So it was already complicated, and now we're just trying to kind of disentangle it. And as I said, I think thinking is pretty new on this stuff. You might think about validity the way you might have learned it, this idea that does the instrument measure what it's purported to measure, where validity was a function of the device. Is that a valid device? But I want you to think about for a second is when you learned about validity in the context of research design, so you learned about internal validity, external validity, statistical validity, right? If you learned the Shadish, Cook, and Campbell typology, it was about the reasonableness of the inferences that were being made from a study. And so updated thinking about validity in measurement science is also trying to move away from this notion that a test or a device could be valid, and more to this notion that it's the interpretation of the measurements or the scores that are valid or not, right? When you think of the word valid as meaning true, which is what valid means true. Validity means sort of the truthiness of some proposition. So instead of a measurement device being valid, right, because that's silly, the measurement device itself we know is going to have error in it, potentially not have sampled the entire conceptual domain. The real issue with measurement devices is that they're person-centered, right? So a sample of 100 people today, how could that device be said to be valid when it might yield different patterns of correlations, in terms of concurrent or divergent validity if I measured it in a different sample of 100 people a month from now? So I think the idea of updating the notion of validity as being a function of devices, measurements, scores, scales, or whatever, and rather making validity a function of interpretations is a really important one. And it also, to some extent, does away with all of those individual pieces of, what kind of validity is this? Oh, it's predictive. Oh, it's concurrent. Oh, it's divergent. Instead of that typology, we're able to just say, what kind of evidence could I bring to bear on the question of whether or not this inference that I'm trying to make as a function of this measurement that I took is a valid inference. So in order to move forward with their discussion of reliability, we're going to do a correlation refresh because you can never get enough correlation. So I'll just remind you that when we say correlation, generally what people are talking about is Pearson's R, which is the linear association between two continuous or quasi-continuously distributed variables. The word correlation itself is really important. The concept is really important to understand. So we're gonna look at it sort of computationally, and it's going to give us some tools to think about covariance and variance that can help us think about what reliability means. So if you'll just be patient for a couple slides, we're going to do a little bit of computation. So what I plotted here is an X and a Y variable. I've just made up height and shoe size. Height is a continuously distributed variable, right? And in thinking about our discussions of variables as they really are, as real things out there in the world that have some theoretical and empirical random distribution, height is one of those variables. Biologic variables that are multi-genetically caused are the variables that tend to be normally distributed. And so people often wonder what's so special about the normal distribution. Why do we rely so much on it? Because it is a frequently occurring distribution for people. And the other point I'll make about that is when I said quasi-continuous, because shoe size is actually, I guess, an ordinal variable, a count variable. But it does reflect an underlying continuous dimension, which is length. And so, as we've discussed in class, if you're pretty committed to the proposition that the underlying variable is continuous in nature, and that you've done a reasonable job of trying to capture its measurements, then it's reasonable to treat it as a continuous variable for the purposes of something like linear association, like we have here. So on the right is a scatter plot. I know you guys know what a scatter plot looks like. The x-axis is plotted with the x variable, the y-axis is plotted with the y variable. What is not shown on this plot is if you looked at the means of the x and y distributions, if you sort of put a cross in the middle of that plot and think about what it means for x and y to be positively linearly related like they are here, it means that increasing values of x are associated with increasing values of y. Another way to say that is if you tend to be above the mean on X, you're going to tend to be above the mean on Y. If you tend to be below the mean on X, you're going to tend to be below the mean on Y. I'm making a big deal out of that particular interpretation because it's integral to the conceptual definition of what a correlation coefficient is. So if you look at the grid here, you'll see that I have the X variable plotted. At the bottom is the mean and standard deviation of X, so 66.4 and 4.37. And if you think about what it means to be above or below the mean, so for example, the first score, 72, is 6 units above the mean of X, approximately. The standard deviation of X is 4, and so the z-score reflects the fact that a score of 72 is 1.3 standard deviations above the mean of X. And so the next column shows the z-score associated with each X, which, as you'll recall, is the score deviated from the mean. So it's a distance from the mean expressed in standard deviation units divided through by the standard deviation. So those z-scores reflect for any given X score how far above or below the mean it is. The closest one to the mean, I guess, is the 0.37, right? So 66.4 is the mean. The score of 68 is just barely above the mean. It's 0.37 standard deviation units above the mean. The mean of any z-score distribution is always 0. That is what a z-score is, right? It is a perfect linear transformation of distance from the mean such that it's equally balanced around the mean with positive scores and negative scores. So the mean of any z-score distribution is always 0. You can see the same thing was done for Y. The mean of the Y distribution is 9.125, or a shoe size of just above 9, with a standard deviation of 2.07. So the next column shows the z-scores associated with all the Ys. Again, nothing more than the distance each of the raw Y scores is above the mean of its own distribution. And the reason we're spending time talking about this is because what it means for two things to be correlated, if you think of it conceptually, is if you tend to be above the mean on X, you'll tend to be above the mean on Y. That's for a positive correlation. For an inverse correlation, obviously, it means if you tend to be above the mean on X, you'll tend to be below the mean on Y, but conceptually, it's exactly the same. So the final column shows the product of the two z-scores. So that value, 0.545, is the multiplication of 1.29 and 0.42. So what it expresses is that pair of scores, how associated they are in terms of tending to both be above the mean. If the z-score for a shoe size of 10 were larger, i.e., if a shoe size of 10 was a full standard deviation above the mean, then the product would be larger, right? You'd have a larger positive number. So the 0.545 reflects the fact that there is a tendency for that score of X to be above the mean and a tendency for that score of Y to be above its mean, but not necessarily a very strong tendency. So the column at the far right is the product of all the z-scores. So one thing to note is that they're all positive, which means every product, every multiplication of z sub x and z sub y was positive. All of the x's that are above the mean all of the x's that are above the mean on X are associated with y's, which are above the mean on Y. If any of those products had been negative, it would have meant that one of them was positive and one of them was negative. So the column at the end is a reflection of the tendency of each pair of scores to occupy a similar place in its own distribution. And at the bottom is the sum. The sum of all of those z-score cross products is 6.2. That is the total of the tendency of pairs of scores to occupy similar places in their own distributions. The correlation is nothing more than the average tendency for pairs of scores to occupy similar positions in their respective distributions. So we take the sum and we divide through by some factor of the number of pairs that there are. And for the correlation coefficient, it's n minus 1. So you take the sum of the z-squared cross products and divide by n minus 1, and that gives you the correlation coefficient. It is a literal expression of the degree to which pairs of squares tend to occupy similar positions in their own distributions. So we're going to look at something else, which is essentially the exact same thing. It is almost the exact same grid, the same columns for x and y, the same z-scores for x and y are there. They haven't changed at all. But there's a new column now that says, just to the right of x, you see x minus x bar. That is the distance of each x above the mean in actual units, right? So 72 minus 66.38 is 5.63. It is a z-score of 1.29 because if you divided 5.625 by 4.373, right, the distance of the score from the mean divided through by the standard deviation of that distribution, you would get 1.29. So that column is just an unstandardized expression of distance of each x score from its own mean. It's the unstandardized expression of that. The z-score is the standardized expression of that. So the same thing is true for the y. The y minus y bar is the distance of each y value from the mean of its own distribution in an unstandardized form, and the z-score is the distance of each y value from the mean of the y distribution in a standardized form. So at the very end, instead of multiplying the z-scores together, I've multiplied the unstandardized distances together. And we see that the sum of the unstandardized cross products is 56.13. So this is exactly what we did before, just in an unstandardized form. But it's important because that value, the covariance of x and y, is defined as the sum of the distances, right? So the sum of the distance of each x from its own mean multiplied by each y from its own mean, right? Summed together, which is the 56.13, divided by that same factor of n, or n minus 1. And so what we've got here is an unstandardized expression. Instead of the z-score cross products, we've got the covariance. And it's not any more interpretable than the sum of the z-score cross products was. It's 8.02. But if you divide that 8.02 through by the product of the standard deviations of the two distributions, so that's what is shown below, Rxy equals the covariance of x and y divided by s sub x at s sub y, you get the correlation coefficient. This is just an algebraic rearrangement of the exact same equation. It's just done in a different way with some terms moved around. But it allows us to isolate something interesting from the correlation coefficient, which is the actual value of the covariance of the two variables. So remember, the covariance, it's at the top on the right, is nothing more than the average of the unstandardized distances, or the unstandardized degree to which pairs of scores tend to occupy similar positions in their own distributions. And that covariance value is important for thinking about some reliability coefficients, and that's why we're spending some time on it. So if you took intro stats with me, I would have taught you the z-score version of correlation because I think it makes more sense, right? The sum of the standardized distances of all of this, the degree to which pairs of scores tend to occupy similar positions in their respective distributions in a standardized way. The covariance is the exact same thing. It's the tendency of pairs of scores to occupy similar positions in their own distributions, but the unstandardized version of that. And we're going to look at how we can use that to think about reliability. So the next slide is nothing more than a different expression of the exact same thing that says the correlation of x1 and x2. So, you know, we're used to the thinking of those values as x and y because we usually learn correlation because we're getting ready to learn regression, where it makes sense to have a clear x and a clear y. It's more common in correlational analyses, though, and it's entirely common in the kinds of reliability analyses that we're going to look at, to call the two things that you want to look at the relationship of x1 and x2. So that's all that says on the left is the correlation of x1 and x2. is nothing more than the covariance of x1 and x2 divided by the product of the standard deviations. It's a little trickier here. It's rearranged again. The standard deviation is the square root of the variance, right? So what you see in the denominator is actually the variance of x1 multiplied by the variance of x2. And then you take the square root of that because the variance is the square of the standard deviation. However, if you re-express that equation, so the second one next to the equal sign, as the variance of t divided by the variance of, this should have been next. So let's go to the next slide and then we'll come back. What the t is it's expressing this idea that any x variable's measurement is the sum of the true score on x plus the error associated with x. So these slides are a tiny bit out of order. We'll come back to this. Okay, so here it is. So this is an expression of that thing, the exact thing that I was just saying from the latent variable perspective that we've been talking about. Remember, x's are always boxes. Observed variables are always boxes. So in this depiction, we have some measured variable x. And we're saying, well, what goes into x, or what comprises x, or what causes x is one way to think about it in reflexive latent variable theory. X is comprised of the extent to which the measurement of x has managed to capture the true value of that case on the underlying latent variable. And we call that value t. T always stands for true score. And so we're saying with this picture that the measurement of x is to some extent caused by the true score on x, right, which is called t, that represents the amount of the quantity that's being measured, that the case that x is measured from contains, along with some error. I don't know why, there it is. So any part of x that isn't caused by the underlying true amount of the quantity that's being measured, t, has to be expressed as error, right? It's just error. So the tiny equation on the bottom right that says x equals t plus e is actually a tremendously important and influential equation to think about from a measurement theory perspective, because it is acknowledging all the time that any measurement x you take contains error. This is just a visual depiction of the idea that measurements always contain error. And that's why, sorry, this was a little bit out of order. If we go back to this slide, which is just the slide before, that's what you see in the second equation, which is saying that, well, let's look at the first equation. The covariance of x1 and x2, right, where every x contains both a t and an e, right? Every x contains a portion of itself is comprised of true score variability, but a portion of the x is comprised of error. And that's why in the second equation, the re-expression says, what if we could capture the variance of just the true scores? And then again, if you look in the denominator, we're saying, because these are the standard deviations of x, right, we're just re-expressing this notion that all x measurements are comprised of both t and e. And this gives you the conceptual definition for reliability, which is that reliability is the portion of the x covariance, that's true score covariance, divided through by the portion of x score, or the total covariance, the total covariance in x, which is t plus e. So that's why we spent all that time on correlation, was to sort of say, let's really think about what it means for an x score to be measured. Oh, we acknowledge it has true score variance and error variance. Let's think really carefully about what it means for two x's to covary with each other, which necessarily implies that a portion of the covariance is true score covariance, but a portion of the covariance is error. And that if we could try to figure out what is true score covariance and what is error covariance, we would know perfectly what the reliability is. And that's the conceptual definition of reliability. And that's the reason why when we assess reliability, we always assess it with a correlation coefficient. So this is just the slide we just looked at, showing that visually. And this is the formal definition. The reliability is the proportion of observed variance that is true variance. So that's the classic definition of reliability from the measurement perspective. This is the same picture as we saw before, just showing that x is always a function of t plus e, and that the reliability of x is the proportion of all of the variance that's true score variance. And it's for this reason that test-retest reliability is seen as the gold standard for reliability estimation, because it's the same x, right? It's the only reliability situation or the only reliability criteria where you're measuring the same x twice. So this is not about the reliability of, parallel forms reliability, which are different versions of items that are supposed to measure the same thing. This is not criterion or predictive, where you're associating an x with something that is only maybe weakly related to it. At its core, reliability should be assessed with test-retest, right? Where you know that you're assessing the exact same x again, and that the only difference, as long as, and it's a strong assumption, as long as there can be assumed or expected to be no change between testing occasions, then you have a way to estimate the reliability of the x by measuring it twice. So that's shown here with the sort of latent variable symbology that we've been looking at. X1 is x measured at time 1, x2 is x measured at time 2. We know that since it's the same x with no expected change between the measurement associations, that the proportion or some portion of observed x1 and x2 is true score variability, and that what's left over is unique or error variability in x1 and x2. And although it's kind of a subtle point that we don't really need to apprehend for the purposes of this class, if you do get into any structural equation modeling, you'll learn that one of the strongest assumptions of structural equation modeling is that the errors are independent of the true score. They have to be independent of the true score, right? So, because x is nothing more than an additive function of t plus e. So there can be no part of e that's also part of t, right? Because that messes up that simple linear additive model. And the other strong assumption for this kind of modeling is that the errors are uncorrelated with each other. And that's a more difficult assumption to meet, because what we're saying here is at time 1, we measured x, and we said it's a function of the true underlying standing on that trait, whatever it is, on that latent variable, and we call that t. And then whatever wasn't part of t, we lump into e, and we say we don't know where it is, we don't know where it's coming from. We assume it is random across people and not systematic, and we assume it's uncorrelated with t, everything in the circle, which is called e, or unique variance, can't be assumed to be correlated with everything that's causing x2 or x at time 2 that isn't also true score variance. And so you'll see in structural equation modeling, we have a way to try to figure that out. But in reliability estimations, we have to make that assumption. And so if you think about what might be causing x that's not t at time 1, right? That's random across people. It's the things that contaminate observations or that contaminate measurements. In the self-report paradigm, it's things like people who had a bad day, people who had a good day, the room is hot, I got bit by a dog, my spouse yelled at me. It's random variability. Is it reasonable to assume if you came back a week later, measured the same people, right? Because that's what you're doing, is measuring the same people in the test-retest model. measure them a week later with the same measure, that the things that would be driving the second measurement outside of their true standing on that variable, so all of the E that's not T, all of the E2 that's not T, has to be assumed to be unrelated to all of the E1, all of the E at time one. So that's just a conceptual way of thinking about what these errors mean, what reliability means, and I think what I hoped you would take away from this is why test retest reliability is seen as the gold standard of reliability in this view.